All right, welcome to the AWS Sense Module 4 stick welding. This is shield metal arc welding. Get right into it here. It's welding equipment. So we've got a machine, we've got a power source, and they're showing you basically the flow of electricity. All right, so we got power supply indicates whether you got, or dictates whether you got AC, DC electrode positive, or DC electrode negative. AC will be alternating current. I mean, the current would switch directions. In America, it's 60 times per second. That's a hertz for us. DC electrode positive, which is this top one, if I push the, there we go, would mean that my electrode, my stinger was positive and my ground was negative. DC electrode negative would mean my electrode, DC electrode negative, my stinger was negative and my ground was positive. Like electricity is the flow of electrons. So in DC electrode positive, the electric is actually jumping from the ground into my hand. And I think I got an animation here. Look at that. The electric is flowing from the ground into my hand and back to the machine. On DC electrode negative, my stinger is negative. We don't stick weld like this. We TIG weld negative. But the electricity is then jumping when I TIG weld from my hand to the metal and back to the machine. Now, why? Why do we stick weld on electrode positive? It puts 70% of the heat on our electrode. It helps melt the electrode and make that part of the weld. When we TIG weld, DC electrode negative, the tungsten can't handle 70% of the heat. So the tungsten is the heat. It pushes that into the base metal. 70% of that heat, again, depending on the flow of electricity, the receiving end, the positive end, receives most of the electrical heat. So TIG, even the tungsten couldn't hold that. That's why we TIG weld on DC electrode negative. If you don't believe me, go DC electrode positive and strike up with your TIG rig. See what happens. Rectifier. A rectifier is inside of your welding machines, and that's what gives you the DC current. All right. So typically, because of what we're doing, we're taking a copper spool and we're spinning it in magnets spinning them in copper coil. We're going to get typically an AC type of current. If you've got a rectifier, that's going to allow you to take that AC current and give us direct current. So a welding machine like this one, for example, that is a DC machine, has a rectifier in that. And here's an AC wave. That's what it's showing you right there. We're changing the electric, and for America, again, that's 60 times. There you go. 60 times per second. That is a hertz. SA welding machines have rectifiers, and they are powered by gas or diesel. So that's kind of cool. It keeps them pretty versatile right here. This is a diesel right here. This is a Perkins diesel. Matter of fact, it's Sam Johnson. This is we gave this one away at KWI. That's little Lucas P's there, Sam's sidekick. Duty cycle. What is duty cycle? Duty cycle is the amount of time a machine can operate at its maximum capacity before it overheats and shuts itself off. Okay, so it's given to you in a percentage, like these buzz boxes. Maybe they're 30%, or the example here is 60% duty cycle. Well, if these are AC buzz box 225s, that means they can weld at 225 amps for 6 minutes out of 10 before they shut down. All right, so that's 60%. 60% of 10 is 6. I can weld max 225 for 6 minutes, and it's going to quit on me. It's going to shut itself off, and the fan's probably going to keep running to try to cool itself down. But you're probably going to be out of business for 10 minutes till it gets cool enough to let you weld again. Typically, your machines don't shut off. Why? Because you're not welding at their max amperage range. All right, so you buy a 225, but you only weld at 100 amps. It'll never shut off. Stick welding does require electricity. It requires a base metal. It requires a filler metal. All right. It does not need a gas supply for shielding. Where is your shield gas coming from? This protective gas envelope around your weld is coming from the flux on the outside of the core metal. All right. So the flux provides the protective atmosphere. So yeah, here's a good picture of that gas bubble that's created. It allows that weld to cool before it's introduced to the oxygen in the air. All right. So the flux does 3 things for us. It stabilizes the arc, it makes it shoot straight, it protects the weld, and it cleans the base metal. Actually, it floats the impurities to the top, and that's slag. All right. So that's what your flux does for you. If you don't believe me that it stabilizes your arc, then try to weld without any flux on and see what happens. The arc goes crazy, or it sticks on you real bad. So it definitely controls that arc. And without flux, you're going to get porosity because you have no protective envelope, and that slag's not going to do its job either. Arc length is the distance from the tip of the electrode to your base metal. And typically that's supposed to be the diameter of your rod. So if this is an 1/8 inch rod, then I should be an 1/8 inch off the plate, okay, from tip to base metal. If I'm longer than that, then I'm going to long arc. My temperature is going to feel hotter, and typically that's going to cause excessive spatter. If I short arc, it's going to feel colder, and if I get too close, what's going to happen? I'm going to stick it. All right, so that's arc length. Again, should be the electrode diameter. If you're at the electrode diameter, you're going to get the amperage that you're set on your machine. So if I got 100 amps dialed in with an 1/8 inch rod, and I'm an 1/8 inch off the plate, then I'm going to get 100 amps. If I float bigger than 1/8 inch, 532, then I'm going to get hotter. It's going to feel like 105 amps. If I get shorter, 332 arc length, it's going to feel colder, maybe 90 amps. So I can play with my amperage, my heat, by long and short arcing. All right, some tips and tricks. Backstepping. Occasionally we get crater cracks. So when we pull out of the end of the puddle there too quick, we leave that crater dimpled. That dimple causes a depression. It causes stress risers, and that'll spider crack, a crater crack right there. So backstepping, if you can see the picture here, what's happening is I started here at the number 1, and I welded out. And then I skip back here to the number 2 and welded to my number 1. Then I skip back to the 3 and welded to my number 2. So my last weld, I'm going to start here at B, and I'm going to weld to 3. And what I've done is every time I ride my new weld up on top of my old one, I'm filling that crater up. All right. So pipe, typically you never have the problem of crater cracks, because you start pipe at the 6, come up to the 12, and you start pipe at the 6, come up to the 12, and you overlap them. You toss them on top of each other so the craters are full. Arc blow is a crazy phenomenon that is caused by the magnetism of DC welders. It only occurs on the DC side. Basically what happens is it honestly feels like you have no flux on your electrode. Your arc wanders. It goes kind of crazy. It deflects. It typically happens because those magnetic force fields are concentrated in the corners of the weld. And they say, what do you do to fix it? You can switch to AC, which typically you can't do it because you got a DC machine or you're welding 6010s, or you can adjust your amperage up or down to try to pull some of that magnetism out of it, or you can change the ground location. So if you're welding towards your ground, then move it away. If you're welding away from your ground, then move it towards. But play with the ground and try to pull that magnetism out of that. All right, let's label a shield metal arc welding process here. Looking at A, that's going to be your welding machine. They're never going to call it that. On AWS, they're going to call it your power source. All right, B, that's clearly pointing at your 6010 rod. Okay, so that's your electrode. And if B is your electrode, then technically, then C is your electrode holder. We're going to call that something cool like stinger or whip. All right, but electrode holder is more technical. D, it's going to be my arc. All right. E, that is my work lead, right, or my ground cable, but they're going to call it a work lead. AB is going to be my electrode lead, and AC is going to be my piece of metal, or my base metal, my work. All right. So if you need to pause that, you'll definitely have this diagram on a quiz, so know these things. Now, we've blown it up. We've gone this D picture here, real close, the arc, we've blown it up, and we're going to look at these all piece by piece. So if A and B together is my electrode, then A is looking at that outer piece, that is the flux, and B is the core wire on the inside. All right, so it kind of broke that rod inside and outside. C would have to be that protective gas envelope, that atmosphere that's keeping my weld protected. D is my weld pool. All right, that's that liquid orange that you're looking at. E is going to be my solidified slag on top. AB is going to be my weld metal, right? That's my weld metal underneath, cooling, solidified weld metal. AC, I'd like to call it arc too, but they're not going to call it arc. They're going to call that weld droplets. If you can see, it looks like rain in there. That says your electrode is spitting onto the base metal. AD, if you can see, that basically that looks like a measurement, how much bite or depth I've had as I chewed into my base metal. So they're going to call that depth of penetration. And then AE is my base metal, my workpiece again. So if you need to pause this, do it, because this is definitely going to be on the quiz, and that's a lot of points right there. So make sure you got these straight. All right, get into our welding stinger and cable. So basically, this is telling you, here's a stinger, right? 300 amp. You got your insulators on there, and there's your ground. You got to have these two pieces, and they're going to be connected with cable back to your power source, back to your machine. What about that cable? You guys don't know much about it, but we can buy it in what they call gauges. All right, so that's going to be pound sign and a number. That's a gauge. This is 8 gauge, 4 gauge, 3 gauge. And they're going to have what they call aught cable. If you go down here, this is 1 aught, 2 aught, 3 aught. That's pretty big. Most of us get 1 aught cable. All right, a 1-aught cable, so it'd be good for up to 300 amps. What we're trying to show you here is the further you get away from your machine, 50 feet, 100 feet, 150, 200, the bigger the cable has to be. And gauges run backwards. Think of like metal, needles for calves or something like that. You know, on metal, 14, even though the number is bigger, 14, the gauge is actually smaller. So 14 is smaller than 12. 12 gauge is thicker. Same thing on, you know, needles for calves. If you go to Hinton Mills and buy a 10 gauge needle, a 10 gauge is much bigger, even though the number is smaller. 10 is bigger than 12. All right, and that's what's going on here. So a 4 is bigger than an 8. The cool thing is once you get to the aughts, it's back to true again. All right, so here 4 is bigger than 3. 3 is bigger than 2. 2 is bigger than 1. All right, but when you talk about plain gauges, and that's just the pound with the number sign, the number there, it's backwards. All right, so we're getting bigger as we get smaller, and then in aughts, we're getting bigger as we get bigger. And the main thing to know is that the longer the cable is, the larger the diameter needs. It's going to happen. It's going to resist you. It's going to give you ohms. It's going to heat up in resistance and start smoking or something like that. So you don't want to make sure the right thickness of cable with the amperage you need. And again, there you go. So gauge number gets smaller as cable gets bigger. All right, and then the aught gets bigger as the cable gets bigger. So if we're talking aughts, you know, 2, 3, 4, that's getting bigger. Here we're getting bigger, but the number's getting smaller. 8, 4, 3, still getting bigger. The cable's getting bigger, but the number gets smaller because gauge is backwards. All right, electrode classification. We're going to take a 7018, we're going to break it apart. We're going to show you how to read this thing. So the A means tensile strength, and that is in 1,000 pounds. So this would literally, we add 3 zeros. So 70, 000, 70,000 pounds of PSI, pounds per square inch of tensile. And tensile means pull apart. So you put this thing in a machine and try to pull that rod apart. The rod would not come apart. It would not snap until it reached 70,001 pound. All right, so that's tensile strength. The B section here, so after the first 2 digits, and this can be this can be 3 digits. There is such thing as 11018. That'd be 110,000 PSI. So in this slot right here, in this B slot, we have a number 1. This stands for your welding position. Welding position. Now I know 1F means flat, but think of a 7018. Let's backwards plan it. Think of a 7018. How many positions can you weld a 7018 in? All positions, and that's what a 1 means. A 1 means all positions. All right. If you had a 2, a 7024, that would be a flat and horizontal. All right. And if you had a 7048, a 4 in that position right there, a 4 right there means we can weld everything but a vertical up. So it's too wet. It won't climb a hill. It'll go downhill. It won't go up. All right. So 1 is all positions. 2 is flat and horizontal. 4 is everything but a vertical up. So what's this last number mean? The last number is C here. In this case, it's an 8. That's iron powder, low hydrogen. It is your chemical composition of your flux, and it also tells you the polarity. All right. So polarity and flux composition. There you go. If it can be used on AC, DC electropositive, or DC electronegative, and the recipe, the cake mix for what goes on the outside. All right. If you had a suffix, so this is an E, that stands for an electrode, 8018 -C3. C3 means what? We got A's, C's. So this is a nickel rod. Yeah, so it's a nickel rod, and then how much of it is nickel, I guess. It would be that 3 right there. So so if you have a suffix, B's are common in boilers because you're looking for that chrome moly. The chrome gives you the resistance to rusting or weathering, right? And the moly is the heat resistance, the low creep. So if you had a suffix, that's what we're looking at. There's some manganese moly, other carbon moly. So you can have suffixes too, and that just changes the recipe slightly. So a little more detailed here, not asking you to memorize this, but just know there's not much of it in the cookie batter. Look at this, so it's pretty basic. Look at all your flux coatings. Even though we change them, cellulose, sodium, cellulose, potassium. So 2 of them use cellulose, just the second ingredient that's different. And these 2 second ingredients are used in other mixtures, titania sodium, titania potassium. So look, you use the potassium and sodium again, we just mix and match. Titania iron powder, low hydrogen sodium. All right, so we're using sodium again. Look at that, sodium, sodium, sodium. Low hydrogen potassium, potassium, potassium. Then we have iron powder, iron oxide. Now, we already used iron powder once, And then iron powder, low hydrogen. So there's low hydrogen, there's iron powder again. So really there's only like 6 ingredients. And the way we mix and match them tells you what polarity, and then it gives it different characteristics. So a 6010, DC electrode positive, all positions, and that's only because that 1 right there. That 20 is flat and horizontal only. And look at the characteristics, deep penetrating flat beads. I think there's 2 that they're, yeah, I'm going to go ahead and highlight these so you got to lock those in. The thing on the quiz you're going to have, it's going to ask you for specifics. It's going to say, what is an AC rod that is deeply penetrating? You're going to say, hey, 6011, that's for sure. They're going to ask you, what is an AC rod that is shallow penetrating? You say a 6013. So just know that that last number on a rod tells you the cookie recipe for how to make the flux, and then it also dictates our polarity, all right, which together tells you what kind of characteristics we have from that weld. A lot going on. Now, to further confuse you, just kidding, we're going to explain it, but to further confuse you a little bit, every rod is broken down to what they call an F group. All right, and as you go up, that's what that arrow is showing you. AWS says harder to use as they go up. So an F4 is harder to use than an F3, harder to use than an F2, is harder to use than an F1. So if you get on a job and qualified with an F1 rod, that's the only rod you could use. They're not going to let you go up. But if you get on a job and qualify with an F4, they're going to let you weld with any of these rods below that. All right, so let's see what the F1 rods are. My guess is they're going to be easy ones, right, because they're at the bottom. And easy positions are what? Flat and horizontal. So they're going to be, look at that 2. 6027, 6024, a 7024 be the same thing. That 2 indicates that this rod can only be used in the flat and horizontal. All right, so that's a fast fill. An F1 is a fast fill. It's really, really wet and runny, and it fills up fast. That's why they can only be used in the flat and horizontal. All right, so if you qualified on a job with a 6024, you couldn't weld with anything above it. All right, my bad, went the wrong way. Fill freeze, fill freeze. These are all position, medium deposition, penetration, excellent for sheet metal, bead ranges of smooth, ripple free to distinct, medium slag, easily removed. 60, 12, 13, and 14. So your 12, 13, and 14 series are F2, fill freeze. All right, so we haven't seen anything we recognize yet, right? So where are our 6010s hiding? Where are our 7018s hiding? Which one do you think is harder? You think a 7018 is an F4, or you think a 6010 is an F4? 6010s and 6011s are F3. They are fast freeze rods. So your 6010 and 6011 are F3. All right, and it describes them pretty good here. Deep penetrating, these are our root rods. Arc has a lot of fine weld spatter, that is true. Bead is flat to distinct ripples, yes. Slight slag, difficult to remove at times, yes. Arc is easy to control, good for overhead and vertical, excellent. Which leaves our low hydrogen rods up top, and there you go, you found your 7018. So this rod is awesome. It prevents hydrogen cracking because it's low hydrogen, and it produces dense X-ray quality, excellent notch toughness, ductility. I mean, 718 by AWS standards is the hardest one. If you qualify with the 718 on a job, then that QC should let you weld with any of these rods below. So know for sure which is which. So your F3 rods, that's a 6010, and F4 is your 7018. Electrode care, we're going to put our electrodes, our low hydrogen, in the oven. The oven has to stay at 250 degrees to keep that hydrogen baked out of the rods. All right, so even though they're hydrogen free, they can still allow the hydrogen to creep into them. So don't do it. Cellulose, 6010s and 6011s are stored outside the rod oven. To reduce waste, burn your rods down to the numbers. Don't burn past the numbers because your QC still has to be able to tell if you were welding with the right rod in the right location. All right, let's review. We're wrapping this up. 6013 produces a weld with shallow penetration. True or false? That is true, right? Because it's the 6011 and 10 that are deep penetrating. They're the punch rods, the root rods. 6013 is basically a 7018 on the AC side. Number 2, without a rectifier, a weld machine will produce DC current. That is false, right? You got to have a rectifier. So without a rectifier, a weld machine would produce AC current. Number 3, magnetic forces in DC current cause arc blow. That is true. Number 4, duty cycle is a percentage out of 10 minutes you can weld at max amperage. That too is true. 5, DC electrode positive means electric flows from the electrode to the work. Ooh, electrode positive. And the definition of electricity is the flow of electrons. So I'm going to go with false on that because it means it's going the opposite way. So it's from work to electrode. All right. 6. This is correct. So it's asking, hey, is this order correct from smallest to largest? So we have 4 gauge, 2 gauge, 1 aught, 2 aught. So is that getting bigger as we go? Yes, it is. All right, because the gauges, the number is backwards. And on aughts, the number is true. So that is 100% correct. Number 7, 6010 belongs to the F4 group. We just went over that. So 6010 was an F3. So this is false. There you go. Number 8, backstepping. If you remember, that's that we leapfrogged, essentially, reduces crater cracks. And that is exactly why we use it. Number 9, burnt rod's the number. True. And number 10, 7018 should be kept in an oven after opening the container. And that too is true. 250-degree oven, as a matter of fact. So that concludes our PowerPoint there. Good luck on your arc welding test.